Welcome to the course on advanced power electronics. So we have a now topic 7 on isolated DC-DC converters. These isolated DC-DC converters are classified into three broad categories. The buck converter operations, which comes as buck forward, post-pull buck converter, half-bridge buck converter, and full-bridge converter, and many more. Similarly, boost isolated DC-DC converters configuration are boost forward, boost push-pull, and boost half bridge and boost full bridge. Then we have another category, buck boost isolated converter configuration, starting with flyback converter, cup converter, SEPI converter, and Zeta converter, and many more. So coming to typically application of isolated DC-DC converters, we start from switch mode power supplies, which are used in number of applications, especially the computers, laptop, with the multiple output DC-DC converters. Then typically DC-DC converter for 12 volt regulated automotive switching, then fuel cell, then battery charger, and medical equipment, and many more. So typically the transformers in switch mode power converters, the input output isolation is provided, and this is normally always necessary for 220, 110 mains application, where a degree of safety is provided for the output, and multiple outputs are very easily obtained simply by adding more secondary winding to the transformer. So there are some disadvantages with transformers, such as their additional size, weight, and power losses. The generation of voltage spikes due to the leakage inductance may also be a problem. The transformer turns ratio can be selected to provide output widely different from the input. Non-isolated versions are limited to a range of approximately 5 times. So by selecting the correct turns ratio, the duty cycle of the converter can also be optimized, and the peak currents flowing is minimized. So the polarity of each output is also selectable depending upon the polarity of the secondary with respect to the primary winding. So typically, if you look into a block of switch mode power converter where this isolated DC-DC converter are used, first we have a AC supply which we rectified with the simple diode rectifier, and then filter with the capacitor. Then we have a high frequency converter, which already we talk about with the MOSFET or bipolar transistor, and we get from this DC2 into high frequency AC, where we use the transformer, high frequency transformer. Then we rectified and use the filter for DC output. And of course, feedback goes for the control, so that you can regulate the at least one output voltage of this converter. So this basic building block meant for this switch mode power converters, like supply. And these are typically another block, like you take a 50 to 60 kilowatt power frequency with a MI filter, then rectifier, then unregulated DC, then you convert DC to high frequency AC, then high frequency isolation rectification, then typically feedback, you can call it error amplifier, means is a controller, then PWM output, which goes with the isolation to the switches of your this isolated DC-DC converter. So sometime you have a multiple output, as you need a computer power supply, you have a multiple output like a 12 volt, 24 volt, then you have a 5 volt and even a 3 volt. So depends on the application. You have multiple output also, which really this transformer facilitated for that purpose without much difficulty. Like, of course, you regulate the more precise one, the one output, which is very crucial for going to be processor chip in general. Then the basic control is simply you have output voltage, and then you have a feedback voltage with the amplifier or controller. Then this control is compared with the comparator to give a gating signal for the switching device. Normally, in many of these converters, we use only the one MOSFET or one switching device to which gating signal is provided, like also. Then of course, we have here the control for compensation of error with PWM control, and the typically power stage, and these are the typical, you can how the control goes with the typically of controller, and then PWM controller and power stage and application. So now coming to typically the configurations, in buck we already talked about, we have a buck forward, post pull buck, then half bridge buck, and then full bridge buck. In boost we have boost forward, boost push pull, boost half bridge, and boost full bridge. And then buck boost we have many converters such as flyback, cup, SEPIC, and Zeta. So typically coming to first forward buck converter, we have output voltage N2 upon N1 into D into Vn. So here the turns ratio of primary to secondary comes into picture, so that you can adjust to appropriate desired voltage. Normally the low voltage, sometimes you require like a 5 volt, 3.3 volt, 12 volt, 24 volt from the 220 volt rectified voltage, which is around 198 using this converter. Then you have another forward boost converter. The same converter forward can be converted into boost converter. That comes N2 upon N1 V in upon 1 minus D. Just putting an inductor at the input, it boosts with this as a typically input voltage and apply the higher than input voltage to the typically to the, you can call it the high frequency transformer like. Then we have a flyback converter, which is buck boost converter. Here that's the inductor, which we call it like a typically in buck boost converter, inductor is made couple inductor with the high frequency. You can call it isolation because switching is high frequency, and this is the one of the simplest converter which we have. You can call it only one MOSFET, one diode, one capacitor, and with high frequency transformer, and you can adjust the output voltage according to the turns ratio here. Means of course the duty cycle normally are design order of around 0.5 or even less than 0.5, 0.45 to 0.5, because so that saturation of the transformer is not there like but the major change of the voltage can be done by N1 upon N2 turns ratio of the transformer. Then we have a typically push-pull buck converter. Push-pull buck converter is quite popular converter. Here also we can get 2 dV in, so it's a buck converter, and turns ratio N2 upon N2 can decide the voltage ratio in big way, and usually again the duty cycle is kept very close to the 0.5 in this converter also. Then we have a push-pull boost converter. So by putting an inductor at the input supply, series of the supply, it converts into the buck converter to boost converter, and now the transfer function changes to N2 upon N1 in 1 minus 2D because of this inductor. So initially what we do, we switch on both the devices, and then in that case this transformer does not function in that manner with the cancel out each other, and inductor entire voltage applied to the inductor, and then we switch off one. So this inductor voltage plus input voltage boost and then applied to the 1/2 winding, we transfer the energy to the second. In the second half we do the similarly for another half. That's why 2D is involved here like. So this takes care, like typically you can adjust you can boost by controlling the voltage output for the purpose only control, but turns ratio mainly decide the output voltage. Then we have a full bridge converter, which really we, typically we have a input, half bridge converter. So we have input midpoint of capacitor and 2 devices, and then accordingly secondly of course we can have a simple rectifier or forceful rectifier at its own with the LC filter with the freewheeling diode, and here of course the major is the turns ratio N2 upon N1 D into V1 by 2. The half voltage is applied across typically across the winding. Then we have a half bridge boost converter. Like here we have just a coupled series inductor which really boosts the voltage, and then we have typically a transformer, high frequency transformer. So here also turns ratio decide the major voltage ratio. Of course the boosting is there in 1D. Here this input inductor comes into which provides the boosting or current source for this converter. Then we have a full bridge buck converter, which all output is N2 upon N1 2D V in. It's a simple, you can call it the full bridge converter. Then we have if you put in series inductor, like in the input, it gives the boost operation of this bridge converter with the again turns ratio decide the main ratio N2 upon N1 Vn upon 2 upon 1 minus T. So what we do, so either we switch on 4 devices or 2 devices, we short circuit the input inductor, and then we switch diagonally the 2 devices into half cycle, which really provide the transformer action to transfer the energy on the secondary, and the inductor voltage get with the input voltage, so that boosting operation take place here. Then we have typically the buck boost converter, cuck converter. Here the inductor which was typically, what we do, we divide the capacitor into 2 parts. So we have an input inductor, MOSFET, then this capacitor we divide into 2 parts, and we have a transformer in between, and then we have a secondary side again, the capacitor and inductor for the filter. So here we have a relation now N2 upon N1, D upon in upon 1 minus D. Of course normally this also we design around 0.5 duty cycle, but the turns ratio gives the main voltage change from input high voltage to low voltage or otherwise like but these 2 capacitor really functions to block the DC component, so that transformer operation ideal in this case like Then we have a CPIC converter. So this output inductor which was used earlier in CPIC, which made couple inductor, and again the turns ratio decided by the main voltage ratio decided by turns ratio V equal to N2 upon N1 dV in 1 minus T. So its operation is exactly similar to non-isolated, which we already discussed in detail. We switch on the device, so inductor energy is stored, and when we switch off, that energy get transferred to typically the secondary like. Similarly, the GTAC converter, here also again the input inductor which was in series with the MOSFET, we made a couple inductor with a proper turns ratio, and it also comes as a buck boost converter N2 upon N1 D upon D Win upon minus T. Here also normally the converter again designed typically again nearby 0.5 duty cycle, 0.45 to 5.5 duty cycle to take a full advantage of, you can call it the kind of a square wave operation of transformer with the ideal operation of the transformer. So of course these are the normal rating. Up to 200 watt or 100 watt we use flyback, then 300 watt must we prefer forward, then we use 2 transistor flyback up to 400 volt, then push pull 500 watt, then half bridge 1 kilowatt and full bridge above 1 kilowatt, and Kaksha peak zeta converter typically we are use typically up to less than up to 500 watt. Then coming to forward buck converter, as you see here the circuit what we already given earlier also, with supply voltage with the typically transformer have 3 winding, one we take as a with series with the MOSFET, another is the feedback winding, you can call it in series with the diode with the opposite polarity, and then we have output winding with the same polarity as the input winding, and which really transfer the output energy, I mean typically, and then the you can call it with the diode we have LC filter through this. You can just see mode of operation when transistor switch is off, how it goes, and switch is on, the diode when switch is off then the diode conducts, and when switch is on the typically diode become reverse bias, and then these are the typical waveform how look like the different waveform for output as well. When capacitor feed the energy, when typically you can call it the inductor current is not there, and then these are the typical mode of operation when you can call it, I mean typically the diode is on, switch on, then diode is on, and then none of the two are on. So sometimes we have 3 modes of operation for DCM operation, like I mean, or we can operate even in the 2 mode, but normally prefer to operate in 3 mode. The advantage of 3 mode is one get inherent PFC, and the second advantage of typically is that the transformer does not saturate, like I mean, or you get the flux resetting to 0, as you can see clearly in the waveform also here. So now coming to the analysis of the single switch forward buck converter. So voltage across the different windings are V1 equal to Vin, V2 equal to V1 N2 upon N1 equal to N2 upon N1 Vin, and V3 is V1 into N3 N1 and O equal to Vin N3 N1. So voltage across the diode is VD3 minus equal to minus Vin minus V3, that is minus Vin in bracket 1 plus N3 upon N1, which is less than 0. So the value of VD3 is negative and it is reverse bias. So where D1 is the forward bias, making the D2 as reverse bias. So the voltage across the inductor is like VL equal to V2 minus V in VO, and that is V in N2 upon N1 minus VO, that is L di L upon dt, and dl upon dt we can call it here is comes to be V in N2 upon N1 minus VO divided by L, or delta IL upon dt, delta T equal to delta IL upon delta T. So change in the inductor current during the on period for delta IL on equal to V in N2 upon N1 minus VO in bracket, so dt upon L. So change in the current of magnetizing inductance is delta ILM equal to V in dt upon Ln, and from these equations current in L and Ln are increasing linearly on period. The current within without transformer you can call it current with the transformer by winding is for Is equal to I1 plus ILM, that is magnetizing current, so ILM plus I2, that is N2 upon N1, N1 upon 2. So during off period the solid phase switch is open and current in L and L1 cannot change instantaneously. For this the continuity of ILM results in I1 equal to minus ILM, which try to reverse the current in current I2, but diode D1 does not allow it. It state from the tertiary winding and in the diode D3, so it feeds the stored magnetic energy in LM back to the input DC source when diode D3 is conducting. So the voltage across tertiary winding is V3 equal to minus V1, and the typically voltage across the winding 1 and 2 and inductors are as V1 equal to V3 N1 upon N3 equal to minus V in N1 upon N3. So V2 equal to V3 N2 upon N3 minus V in your N2 upon N3, and minus V equal to minus VL equal to minus VO, that is L di upon dt, or dIL upon dt equal to minus VO divided by L, so equal to dIL upon dt equal to dIL upon 1 minus d into t. So change in the current of inductor is taken as delta IF during off period, or IL of equal to minus VO 1 minus dt upon L. So under steady state condition total change in inductor current is 0 over a period of, so delta IL on plus delta IL off equal to 0. So under steady state condition the total change in inductor current IL is 0 over a period of delta IL on plus delta I off equal to 0. So substituting the values of IL on and I off from these equations, so it becomes V in ID at 2 upon N1 minus VO into dt upon L minus VO 1 minus d t upon L. Solving these, so it comes VO equal to V in d in bracket N2 upon N1 equal to V in into dn. So where d is the duty ratio and n is the turns ratio, so VLM equal to V1 equal to minus V in and N1 upon N3 equal to LM Li di LM dt, or dLm equal to dt upon dLm upon dt equal to minus V in N1 upon N3 divided by Lm, or delta ILM upon delta T. To avoid the saturation in the transformer, the ILM must decrease to 0 before the next P-long period. So from this equation it can be seen that ILM decreases linearly and D3 ceases conduction when ILM tends to 0. So if Tx is the period to become ILM 0, then delta M Tx equal to V in dt upon Lm Tx equal to minus V in N1 upon N3 Lm. So next, the time Tx from this equation is Tx equal to dt upon N3 upon N1. So the time at which Lm decreases to 0 is Ty, that dt plus the Tx, or dt plus dt in N2 N3 upon N1, or equal to dt in bracket 1 plus N3 upon N1. So from this condition, that ILM to decrease 0 before the start of next period. So Ty is lesser than T, or dt 1 plus N3 upon N1 less than T, or d 1 plus N3 divided by N1 less than 1. Therefore, maximum value of d is restricted to less than N1 upon 1 plus N3. For this case, if N1 equal to N3, and then d must be less than 0.5 to avoid the saturation in transformer. The voltage across solid state switch during the off period is Vs equal to V in minus V1, that is equal to V in minus in bracket minus V in N1 upon N3, or equal to Vs in bracket N1 plus N1 upon N3 for dt less than T, and Vs equal to V in for T in between T or T and Ty. So the output voltage is in forward converter can be calculated in similar manner. A buck converter waveform given in the IC and output voltage having the ripple, and from this capacitor current IC equal to IL minus IR. So for duration of when capacitor current is positive, the capacitor is charging, therefore the charge on the capacitor is Q equal to CV0, or delta QC equal to CV delta V, or delta V equal to Q delta Q C upon delta Q upon C. So the change in charge delta QC is calculated from the ripple in the capacitor by delta Q equal to T by 2 into delta IL upon 2 by divided by 2, or equal to T delta IL upon 8, or delta V0 equal to T delta IL upon 8C. So keeping the value of delta IL as delta V0 equal to T V0 1 minus D into T divided by 8CL, or equal to V0 1 minus D divided by 8 LCF square. So per unit voltage ripple is as delta V0 upon V0 equal to 1 minus D upon 8CL F square. So the capacitor value for a given voltage ripple can be calculated as C equal to 1 minus D V0 divided by delta V0 8 LF square. So similarly, inductance value can be calculated for a given ripple current L equal to minus V0 1 minus D T upon delta IL equal to 1 minus DR divided by F delta IL upon L, where IL equal to I0 equal to V0 R. For boundary condition between CCM and DCM, delta IL equal to 2L equal to 2IO. Therefore, minimum inductance must be to achieve L minimum. So L minimum equal to V in N2 upon N1 minus VO into D upon F delta IL, or equal to V in N2 upon N1 equal to minus VO DR upon 2 F V0. So these are the typically detailed operation of forward converter in different modes, as it's shown. Typically device is on, typically diode, typically the freewheeling mode, then the diode typically on. So all conditions are given here. Like these are the typical waveform for these modes are given here. So now coming to other types of forward DC-DC converter with the two switch. Sometime to enhance the power rating, we use the two switch, where the transformer utilization is much better. Like to other topology, two switch forward converter, parallel forward converter to increase the rating. Like so, advantage is the forward converter is always operated in continuous mode. In this case, the output inductor current, since this produces very low peak input current and output current is small ripple component, and going to into discontinuous mode will greatly increase these value, as well as increasing the amount of the switching noise generated. So since the transformer in this topology transfers the energy directly, there is a negligible stored energy in the core compared to the flyback. However, there is a small magnetization energy required to excite the core, allowing it to become an energy transfer medium. This energy is very small, and only a very small primary magnetization current is needed. This means that a high primary inductance is usually suitable with no need for a core air gap required in the flyback. So the transistors have the same voltage rating as the discontinuous flyback. as a disadvantage, but the peak current required for the same output power is half, and this can be seen in the equation given for the forward converter. Thus, the coupled with the smaller transformer and the output filter requirement means that the forward converter is suitable for use of high output power than the flyback converter range, and is normally designed to operate in between 100 to 400 volt watt range. The disadvantage is that because of the unipolar switching action of the forward converter, there is a major problem in how to remove the core magnetization energy by the end of each switching cycle. And if this did not happen, then this will be a net DC flux building up, leading to core saturation and possible transistor restriction. Now coming to buck boost post-pole DC-DC converter as shown in the circuit here. Both the switches S1 and S2 are switched on alternately in each half of the pendulum period, with the controller width of pulse decided by the duty cycle from the output voltage controller. And these are the typical mode, like how really you can call it the operation with one possible polarity of the transformer and typically with another polarity of the transformers, like the circuit, the operation, how really it operates. One switch on, then none of the on, then second is on, and then another switch is on, then both are again off, or second is on. How the energy take place, in different modes of operation, like typical. And these are the typical waveform corresponding to in different modes of operation. And typically for DCM operation, that was for CCM, how the DCM operation, these are there. So you get even DCM operation in between too, and the typical waveform for DCM operation. The advantage of push-pull converters offers very compact design of the transformer and output filter while producing very low output ripple, and clamp diodes are fitted across the transistor as shown. This allows the leakage and magnetizing energy to be simply channeled back to the supply, reducing the stress on the switches and slightly improving the efficiency. And the emitter or source of the power transistors are both at same potential in the push-pull configuration and are normally referenced to ground. This means that the simple base drive can be used for both, and no costly isolating drive transformer is required in many applications. To disadvantage, the center tape arrangement also means that extra copper is needed for the primary, and very good coupling between the two halves is necessary to minimize the possible leakage spikes. And it should be also noted that if the snubbers are used to protect the transistor, then design must be very precise, since each tends to interact with the other, and this is true for all symmetric driven converter. Now coming to buck half bridge DC-DC converter, here you can see output is your N2 upon N1 as it typically turns ratio D upon Vin, and here also we have in one half one transistor operating, another half another transistor operating to transfer the energy from input to output. And these are the typically different modes of operation, how really take place. Like initially we switch on a one upper transistor and the energy take place, then in the second case we switch on the lower transistor, and then the operation of different modes of operation take place there. And these are the typically the waveforms, how really it goes to in different modes of operation of primary of the transistor voltage, primary and secondary, and transistor currents, like, and the simulated waveform in CCM of this So coming to the analysis in continuous conduction mode of half-bridge DC-DC converter, in the first state switch S1 is on, it apply half the input voltage across the primary winding, and the same time induced voltage in secondary winding output. Charges the output capacity of filter inductor across different components. So Vp equal to Vin by 2 and Vs1 equal to Ns1 upon Np into Vin by 2, and VL equal to Ns1 upon Np and into Vin by 2 minus Vo, and the inductor current rises linearly dIL upon dt equal to VL upon L, that is in bracket Nsi Np into Vn by 2 in minus Vo divided by L. As shown in the figure, the maximum current in Imax equal to I minimum, IL minimum equal plus Ns1 upon Np and Vn by 2 minus Vo dt by 2. So the second stage from dt between dt to t by 2, during which the both resistors switch are off. During this stage current, the inductor reduces. Sorry. So dIL upon dt equal to minus Vo upon L. T varies from 0 to 0.5 minus Vd by into T. So from the equation, the value of I minimum can be calculated as IL minimum equal to IL and T equal to 0.5 D minus D T and equal to IL max minus Vo in bracket 0.5 minus D T upon L. So in stage third, second solid state switch is on and other devices are off, and primary winding voltage is Vp equal to minus Vn by 2. So moreover, in the third and fourth stage, the converter operates in same manner as in the first two stages. So in the alternate method, the integral of inductor voltage is 0 over a p-long period due to repeatable nature as ns1 upon np to vn by 2 minus vo into dt plus minus vo in bracket 0.5 minus d into t equal to 0 results in vo equal to d in bracket ns1 upon np into n equal to n vd in, where n equal to ns1 upon np, the turns ratio being ns1 equal to ns2 into and d the duty ratio of each solid state switch. So for boundary condition between CCM and DCM, delta IL equal to 2IL equal to 2IO equal to 2IO equal to VO upon R. The minimum inductance is L minimum equal to VO in bracket 0.5 minus D divided by 2 VO on R into F equal to 0.5 minus D R into 2F. So the ripple voltage from is equal to delta V equal to VO 1 minus 2D upon 32 LCF square, and per unit voltage VO delta V upon V0 equal to 1 minus 2D divided by 32 LCF square. So the value of output capacitor can be calculated for a given value of ripple voltage across the capacitor. So C equal to 1 minus 2D VO divided by 32 L delta V0 F square. So minimum capacitor for the same voltage can be calculated to be delta V equal to V0. So C equal to 1 minus 2D equal to 64 LF square. So the typically the equivalent circuit of half bridge converter with transformer tap for DCM is from D to DT, for DT to D plus T1, and for D plus T1 between to T by 2. So for the typically D condition T by 2 to T by 2 plus delta T, and for T by 2 plus delta T, and to typical T by 2 D plus D1 by 2. And these are the typically, you can call it the circuit, equivalent circuit of this half bridge converter for the different three modes, like, and typically additional port mode and fifth mode. And these are the typical waveform. Of course, during the whole period period, how really vary the different parameter gate signals of the devices of first and second device, as well as the primary current and the primary voltage, secondary current, and typically the, you can call it inductor voltage, inductor current, also diode voltage, diode current, and all parameters. So the advantage of half bridge is particularly suited to high voltage inputs such as offline application. For example, 220 volt mains AC mains application to use to high speed, high efficiency for 50 volt transistor instead of 800 types needed for a push pull. This allows higher frequency operation. So another major advantage over the push pull is that the transformer saturation problems due to flux symmetry and balance are not a problem here. By using a small capacitor less than a 10 for a DC building of a flux in the transformer is blocked, and only 10 microfarad and only symmetrical AC is drawn from the input. So it has excellent transformer utilization, very low output ripple, and high output power capability. So limiting factor in the maximum output power available from the half bridge is the peak current handling capability of the present day transistor, that is 1000 watt is typically the upper power limit. For higher output power, the 4-switch full bridge is normally used. Disadvantage: the need for 250 to 60 Hz input capacitors is a drawback because of their large size. Furthermore, if numbers are used across the power transistor, great care must be taken into their design, since the symmetry action means that they will interact with each another. The capacitor cost and complexity have clearly increased, and this must be weighted up against the advantage gain. Now coming to buck full bridge DC-DC convert, you can clearly see buck full bridge DC primary side. Secondary side, of course, you can have a bridge, or normally because of low voltage, we prefer to push pull only one diode connector at a time and without output LC filter. And these are the typical modes of operation. Then when your one device is on, then another device is on, and how the secondary, typically the all four secondary diodes and primary devices are on in 4 modes. And these are the typical waveforms, I mean, in different modes in a complete cycles about the primary winding, primary transistor voltage and transistor current, and diode voltage, diode currents. And then, of course, simulate a waveform corresponding to typically all the components and primary, secondary winding. And typically now about coming to how the operation of full bridge take place, and even if you have a typically with the full bridge also how it really, or push pull arrangement also, how half wave rectifier with the primary side. I mean, you can have a different circuit on the secondary side for different output voltage. I mean, very low voltage you can take only typically the half or full. So full bridge DC converter circuit, it composed of a PWM inverter and PWM rectifier. The inverter consists of a transformer and 4 power MOSFETs used as controllable switch S1, S2, S3 and S4. The transistor in each switching leg are drawn by non-overlapping voltages that are out of phase by 180 degree. The maximum duty cycle of the gate source voltage is slightly less than 50%. The waveform of the gate to source voltage will be non-overlapping. Therefore, it is not easy to drive the upper transistor because their gates are not driven with respect to ground. The pulse transformers can be used to drive the upper transistor. So the lower transistor can be drawn by pulse transformer. The pulse transformer driving a transistor S1, S2 may be connected to one output of a control circuit. Similarly, the pulse transformer driving a transistor S2 and S4 may be connected to the second output of the control. The two outputs of control circuit provide non-overlapping voltage of the out of phase by 180 degree. The isolation transformer is not required to store energy. Its magnetizing inductance Lm should be large enough to reduce the current through this inductance. On the other hand, if magnetizing inductance is too large, it requires a large number of turns and is physically large. So ideally, the DC component of the current through the magnetizing inductance is 0. A coupling capacitor may be added in series with the primary winding to achieve 0 DC component of the current through the magnetizing inductance and thus remove the imbalance of the magnetic core or cross conduction and the switching part. And this is typically how really the operation take place of this full bridge with the push-pull arrangement of the different modes like for CCM operation like all four modes and corresponding waveform of this bridge converter. Now for the case of TCM, how the operation take place like a planned waveform correspond. So the advantage, the full bridge is ideal for the generation of very high output power levels above 1 kilowatt, and full bridge also has the advantage of the only require one mesh smoothing capacitor compared to the two half bridge, hence saving the space. In other major advantages are the same as for the half bridge. The disadvantage full bridge has the most complex and costly design of the converter discussed and should be only used where other types do not meet the requirement. So again, the 4 transistors and snubber if required must be implemented carefully to prevent the interaction between them. Now coming to push-pull DC-DC converter, as you have an input inductor along with the two devices and then the push-pull on the secondary side, of course, to take output low voltage. Here first we switch on both the switches so that inductor energy is stored and transformer does not really transfer the energy because of the short circuit on both part of the winding. And when one switch is off, then input voltage and inductor voltage adds and transfer the energy to the secondary side. So for on period, both devices are made on which circulate equal current in both of the primary winding and can calculating EMF of each half resulting in short circuit at the input inductor output terminal. And in off duration, one of the output S1 or S2 are made off. In consecutive half cycle can be so that the EMF is induced in the secondary, which is rectified by full wave rectifier and charges the output capacitor. So when S1 is closed, S2 is open and diode D1 is on and D2 is off. And these are of course the different modes. You can just have a mode of operation. When inductor, both devices are on, inductor store the energy and output is open circuit. When then one switch lower is off and upper is on and it transfer the energy through upper winding. And in other case again, it transfer the energy from the lower winding. So it's simultaneously the first mode takes place in between the two and these are typically, you can call it the in case of push pull, how typically the first, in case of this we switch on first device, the transformer does not operate, and then when we switch off, then we transfer the energy from the S1 to on. So these are the typical modes how really push pull and boost typically the bridge operates like, and these are the push pull boost operation simulation like. So coming to typically the analysis of boost push pull converter, the input output voltage relation can be derived by making the integral of voltage across the inductor 0. So V in dt plus in bracket in V in minus VO N1 upon N2 into 1 minus D to D equal to 0. So this simplify VO equal to V in N2 upon N1 divided by 1 minus D, and that is V in N small n, that is turns ratio, divided by 1 minus D. So from this equation it is evident that the current fed a forward converter we have as a boost converter, and the rate change of the inductor current can be calculated during the period DIL upon dt equal to V in upon L, or delta IL equal to V in dt upon L, or V in D upon FL. The value of the inductor can be calculated from for a given ripple L equal to V in D upon delta IL into F. So per unit inductor current ripple can be calculated delta IL upon I in equal to V in delta T upon LIL, that is equal to R in D upon FL and equal to R 1 minus D square D upon N square FL. The capacitor voltage ripple can be calculated from half time delta V0 equal to delta Q upon C and equal to 1 minus d into I upon C, or 1 minus dVo R FC upon RFC. The per unit voltage ripple across the resistor is delta V upon V0, 1 minus d upon RFC, and the value of output capacitor can be calculated C equal to 1 minus dVo upon RF. And the following relation are doing the spread ID equal to ID1 equal to IL upon NP upon NS equal to ILN, and VD1 equal to VO upon NP upon NS equal to VO in, and VL equal to VN minus VP1 minus equal to VN minus VO, NP upon NS equal to VN minus VO upon small n turns ratio, and VS W equal to VP1 plus VT2, that is 2V0 NP upon NS equal to 2 VO upon N. So for the period when S1 is open and S2 is open, closed, the diode D2 conduct and D1 is off. So following equations are valid. So ID equal to IL, NP upon NS equal to IL upon small n, VP2 equal to VO, NP upon NS equal to VO upon N, and VL equal to VN minus VO NP upon NS equal to VN minus VO upon N. When both the switches are closed, S1 S2 are made on, the inductor current divides into evenly between the two parts NP1 and NP2 of the primary, therefore the net voltage across. So VP1 equal to VP2 equal to 0. So thus the inductor current rises during this period, that VL equal to Vn. So the integral of inductor voltage must be 0 1 P 2 VD in Vn 2 dt plus Vn minus VO and P upon N1 2 1 minus d into T equal to 0. So or Vn VO put equal to Vn and P upon Ns divided by 2 in bracket 1 minus d equal to Vn n upon 2 divided by 2 1 minus t. So rate change of the inductor current from on period is dIL upon dt equal to Vn upon L, and the change in inductor current is as delta IL equal to Vn dt upon L, and value of inductor for given ripple is L equal to Vn d upon F delta IL. So 1 unit ripple inductor current can be calculated delta IL upon L equal to delta IL upon N equal to Vn d upon FL IN, that is equal to R in d upon FL, and equal to typically R divided by 1 minus d, sorry, R L, so R in 1 minus d 2d upon N square FL. So output capacitor voltage ripple can be calculated as delta V 0 equal to delta QC upon C di0 T upon C, that is equal to V0 d upon FRC. The per unit voltage ripple is there, delta V0 upon V0, that is d upon RFC. The value of output filter can be calculated for given voltage ripple, that is C equal to V0 d divided by F R delta V0. So coming to boost half bridge converter, so here we put the series inductor in series with the two transistors, and which really provide the boosting of the input voltage. Then we have a transformer, and these are the different modes of typically operating this boost half bridge converter, like operating different switches. So coming to the analysis of this, the rate change of current in inductor when both switches are on, dIL upon dt, Vn upon 4L, and the change in inductor IL, delta IL on equal to Vn dt upon 4L. Similarly, when only one switch is on, the rate change of inductor 2L is as a dIL upon dt equal to in bracket Vn by 2 minus N1 upon 2 VO divided by 2L. The rate change of inductor current decreases as delta IF equal to in bracket Vn by 2 minus N1 upon N2 VO into 1 minus dt upon 2L. So net change in inductor current must be 0 on the periodic waveform of half cycle. So delta IL on plus delta IL off equal to 0. So substituting the value of inductor from this, so it becomes Vn dt divided by 4L in bracket Vn by 2 minus N1 upon N2 VO into 1 minus dt upon 2L equal to 0, and VO equal to 0.5 Vn N2 upon N1 divided by 1 minus t, or equal to 0.5 N divided by Vn. So which demonstrated that is a boost converter. The value of inductor can be calculated from for a given value of ripple current. So L equal to Vn dt divided by 4 IL, or equal to Vn d upon 4 F delta IL. So for boundary condition CCM between CCM and DCM, delta IL equal to 2 IL equal to 2 IN, and critical inductance value is LC equal to Vn into d upon 8F IN, and that is equal to Rn into d upon F equal to 1 minus d square R upon 2 Fn square. So the ripple voltage in output capacitor can be calculated from the on period when both the switches are made on and no charging take place. The output capacitor feeds the load resistance are delta V0 equal to delta Q upon C, that is I0 dt upon 2C, or equal to V0 d upon 2F CR. The per unit ripple voltage on the capacitor is delta V upon V0 equal to D upon 2 FCR. The value of output capacitor can be calculated for given value triple C equal to dV0 upon 2 FR delta V, and for critical value of capacitor V equal to 2V0, that is C equal to D upon 2 FR. And these are the typical simulated waveform for boost half bridge converters from the simulation. Now coming to boost full bridge converter, we put an inductor in series with the input supply. The remaining remain the bridge. Of course, on the output we prefer push pull because only one diode connected at a time, so that less losses and less drop are there. So first switch on either one leg or both the legs, so that the inductor store the energy, and then we switch on the diagonal switch, avoiding the other typically two switches, and transfer the energy from input to output simultaneously. So these are typically different modes of operation, how the circuit take place in different modes of operation. So coming to now analysis of this boost bridge DC-DC converter under steady state condition, voltage and current of input inductor and output capacitor are periodic in nature. Therefore, the integral of the inductor voltage over the one period must be 0. So 2 V in bracket D minus 0.5 T equal to plus V in minus N1 upon N2 V0 and 2 into 1 minus D equal to 0. So it's simplified V equal to 0.5 V in N2 upon N1 divided by 1 minus D, that is 0.5 V in N upon 1 minus D. So where N equal to N2 upon N1, the turns ratio of transformer in this control scheme. During on period, both switches are made, S3 and S4 are made off alternately to produce the AC voltage for transformer action. So the rate change of inductor current during the all devices on is dIL upon dt equal to Vn upon L, and the ripple current in inductor is V delta Vn V in bracket D minus 0.5 T upon L, when the dt is the period for which the E device is made on. The value of inductor can be calculated for the given ripple inductor current as L equal to V in bracket D minus 0.5 to T on delta IL and equal to D minus 0.5 V in bracket F delta IL. So for the boundary condition CCM and DCM, delta IL equal to 2IL equal to IO in, and LC equal to L minimum, that is in bracket D minus 0.5 in upon bracket F square upon I equal to 2R D minus 0.5 into 1 minus D square upon 2 Fn square, where N R is the V upon IO. The output ripple voltage can be calculated from the period when no charging take place, that is D minus 0.5 T period for each half cycle. So delta V equal to delta Q upon C, that is I0 D minus 0.5 T upon C, or equal to V0 T minus 0.5 T upon RC. So per unit ripple voltage is delta V upon V0 is equal to D minus 0.5 into T upon RC. The value of output capacitor can be calculated for a given ripple. So C equal to V0 D minus 0.5 divided by F delta V. So coming to typically flyback converter, it's the simplest converter, uses one MOSFET mud diode, and the inductor is made the now coupled inductor to transfer the energy from primary side to secondary side. And these are the typically the modes of operation. Device is on and the diode is on, and the waveform typically of this flyback converter in different modes of operation. And coming to analysis for the condition when switch is on, the basic volt ampere equation of inductor is Vn equal to Lm dIL upon dt, or on the rate change of inductor current is as dILm upon dt equal to Vn upon Lm, and the change in current of the transformer magnetizing inductance is delta ILm on equal to Vn dt upon Lm, and the diode is reverse bias and it has a voltage across it. So Vd equal to minus Vo minus Vn Np upon Ns, and V1 upon equal to Vn, and V2 equal to V1 upon Np upon Ns upon Np, and that is I1 0 and I2 equal to. So during this period there is no current in primary and secondary winding of the transformer. The current in the magnetizing inductor rises linearly. So for the condition when switch is under open condition, no current flows from the input to DC source, output diode becomes reverse bias and start conduct. So rate change of the magnetizing inductance is dILm upon dt equal to V1 minus Vo upon Np upon Ns, and the decrease in current in Lm is your delta ILm of equal to minus Vo in bracket Np upon Ns, and that is bracket 1 minus D into T upon Lm, and the voltage across the winding switch and diode are as V2 equal to minus Vo, V1 equal to minus Np upon Ns into Vo, VSW is Vn minus V1, and Vo equal to Vn plus Vo divided by Ns plus Np. This is the major drawback of buck boost converter, where the you can call it switch voltage is the addition of input and output, and ID equal to minus Ip Np upon Ns equal to IL Np upon Ns, and IR equal to V upon R, and IC equal to ID minus IR. So the net change inductor current must be 0 over a one period under the steady state. So it can be expressed delta IL amount plus delta Lm of equal to 0 for V in dt upon Lm plus in bracket minus VO 1 minus dt divided by Np upon Ns divided by Lm. Solving this for VO equal to V in bracket d upon 1 minus d into Ns upon Np or equal to small n, that is turns ratio d in V divided by 1 minus d. So where Ns is then Ns upon Np, the turns ratio of the transformer considering the ideal case when the zero losses. So P in equal to PO, V in equal to IN equal to VIU, that is VO square upon R. Input source current is V IN ILM dt upon T equal to ILM dt, and from this ILM equal to VO square upon V in into dr. So the maximum value of inductor current is ILM equal to ILM plus delta ILM by 2 in bracket VLM V in d upon 1 minus d square R into N square plus V in dt upon 2 Lm, and minimum inductor current is ILM minimum equal to ILM equal to 2 delta ILM by 2, and that is equal to N V in d in bracket 1 minus d square R minus V in dt upon ILM. So for boundary condition between CCM and DCM, the minimum or critical inductance can be IL min equal to 0, typically 0, or ILMC equal to I minimum, that is 1 minus d square R Lm upon 2 F, and inductance for a given current typically is Lm equal to V in dt upon delta ILM or V in d upon divided by F delta IM. The output voltage ripple can be calculated for a condition when output capacitor discharges across the load as delta V0 equal to delta upon C, or I0 dt upon C, or equal to V0 dt upon RC, or V0 d upon FRC. The per unit voltage ripple across the output capacitor is delta V upon V equal to d upon FRC, and the capacitor value for the given value of voltage ripple is C equal to V0 d upon F or delta V, and the critical value of capacitor for delta V equal to V0, C minimum equal to CC, that G upon 2 FRC. So these are the simulated results for the flyback converter, and these are the different modes for DCM operation. And device on, diode on, none of them to on. These are the typical waveform for DCM operation. The advantage of flyback converter is no filter inductor is needed in the output circuit, hence each output requires only one diode and one output filter capacitor. So this means the flyback is the ideal choice for the generating low cost multiple output supply, and the flyback is also suited for the generating high voltage output. The cross regulation obtained using the multiple output is also very good. Load changes on the one would have a little effect on the other because of absence of output choke, and which degrade the dynamic component. The flyback converters have inherently much higher output ripple than the other topology. So this together with the higher peak current, large capacitors and transformer limit the flyback to the lower output application in the 20 watt to 200 watt. Disadvantage of course of flyback, it should be noted that at higher voltage the required output voltage ripple magnitudes are not normally as stringent, as this means that the equivalent series resistance requirement and capacitor size will not be as large. In order to achieve the low output ripple, very large output capacitors are needed with a very low equivalent series resistance. So now coming to Buck converter, only what we do, we divide this capacitor in between, put the transformer, and normally we operate now around 0.5 duty cycle, so that transformer is operated ideally, and these two capacitors block the DC in primary and secondary, and we have input inductor, output inductors, and of course typically the MOSFET and the diode. And these are the different, typically you can call it the modes of operation, when typically device operates and the diode operates, and sometimes we operate even in DC. So during first mode of device is on, the rate change of current primary and secondary are DIL upon dt equal to V in upon L1, that is V in upon L1, and the rate change of current in the inductors, that is delta IL1 equal to V in dt upon L1. Similarly, the rate change of the current in the inductor 2 DL2 equal to VL2 upon L2 equal to minus VO minus VC1 minus NP upon NS upon NP into VC1 upon L2. The rate change of current in L2 is now delta IL2 on equal to minus VO minus VC2 into NP upon NS upon NP VC1 and dt upon L2. So during mode 2, when the device is off, the rate change of current in the inductor L1 L2 are DIL1 upon dt equal to VL1 upon L1 equal to V in plus VC1 plus NP upon NS into VC2 L1, and rate change of current in L1 is delta IL1 off equal to V in plus VC1 plus NP upon NS VC2 into 1 minus dt upon L1. The rate change of the current in inductor 2 DL2 upon minus V upon L2, and rate change of current in inductor 2 delta IL during the minus V upon 1 minus d T upon L2. So net change in the inductor current L1 inductor current must be 0 over the pendulum. So delta IL on plus delta L2 off equal to 0. So substituting the value delta IL on and delta I off, it becomes V in dt upon L1 plus V in plus Vc1 plus Np upon Ns into Vc2 into 1 minus dr T upon L1 equal to 0. Solving this, so we get V in upon 1 minus d equal to Vc1 plus Np upon Ns into Vc2. Similarly, for net change in current in inductor must be 0 over pendulum. Delta L2 on plus delta L2 off equal to, putting a value, minus V0 minus VL1 minus Ns upon Np Vc1 into dt upon L2 plus in minus V0 1 minus dr dt upon L2. Simplify to Vc1 plus Np upon Ns into Vc2 equal to Np upon Ns Pd V upon d. Solving this, V upon Vn equal to d Np upon Ns upon Np divided by 1 minus d, that is small n d on 1 minus d. So it represents the relation as buck for d equal to 0 to 0.5 and boost for 0.5 to 1, which results in buck boost converter. The value of input inductor can be calculated for the given ripple current L1 equal to V in d upon F delta IL1. Similarly, the value of output inductor can be calculated from L2 equal to plus VO 1 minus d T upon delta IL2 equal to plus P0 1 minus d divided by F IL2. So for the boundary condition between CCM and DCM, the average converter average current in the inductor must be greater than the 1/2 of their current, their ripple current. Thus the value of minimum for critical inductance L1C equal to L1 minimum VI IN D upon F square IL IN equal to R 1 minus D square divided by 2D N square F, and L2 equal to L2 minimum PO 1 minus D upon 2F I0 equal to R 1 minus D R upon 2F. So capacitor is charged in each pendulum period by inductor IL2 current ripple more than load average current as IC2 0 equal to IL2 minus IR, and the change in the charge is for charging current H equal to CV equal to delta Q C delta V or D V0 equal to delta Q upon C. So net the change in charge is calculated from the area of current. So delta Q upon half T by 2 delta L by 2 T equal to delta L by 8. Though the ripple voltage at the output filter capacitor is delta V0 equal to delta V upon C0 T IL2 upon 8 C0 equal to VO 1 minus DT square 8 L2 C0. So per unit output voltage ripple is delta V upon V0 equal to 1 minus D divided by 8 L2 C0 F square. The value of output capacitor can be calculated for the given ripple C0 equal to 1 minus D VO divided by 8 L2 delta V0 F square. The ripple voltage across C1 is calculated during off period. So delta VC1 equal to 1 upon C1 for dt to T IL1 dt or equal to IL1 1 minus dt upon C1, that is equal to V IN square d square divided by RCF 1 minus d. The value of input energy transfer capacitor C1 must be calculated for the given value of voltage ripple, and C1 equal to V in N square D1 T square divided by RF 1 minus d delta VC1. The ripple voltage across capacitor C2 is calculated during off period as delta VC2 equal to 1 upon C2 0 to dt IL2 dt or equal to IL2 on C2 into D2 or equal to I0 D2 divided by C2 or V equal to V0 D upon RF C2. The value of output energy transfer capacitor can be calculated for the given value. Output is C2 equal to V0 D upon RF delta VC2. The integral of voltage across inductor L1 L2 must be 0. So L1 equal to V in dt equal to V in plus Vc1 plus Vc2 upon N d1 t equal to 0 or Vc1 plus Vc2 by 2 N equal to Vd V in d plus d1 equal to d1 and L2 equal to N Vc1 plus Vc2 minus V0 d2 plus minus V0 d1 t equal to 0 or Vc1 plus V2 by 2 N equal to V in d plus d1 divided by Nd. So from these equations the input output voltage relation is V upon Vin equal to N T upon D1 and output P upon P in I upon N, that is D1 upon 1 upon T. So average input current in L1 is IL1 equal to IN equal to V in dt D plus D1, that is 2L1 plus I, and current in the output in IL2 equal to V in dt D plus 1 upon 2L2 minus I. So where IL2 dash equal to N square L2 referring to secondary inductance on primary side of high frequency transformer, and IL2 dash is referred to secondary current primary side IL2 dash upon N. The sum of IL1 and IL2 dash from these is IL1 plus IL2 dash equal to V in dt upon in bracket d1 plus d1 by 2L, where L into L1 L2 dash divided by L1 plus L2 dash. From these equations, the value of IL1 equal to IL1 in bracket 1 plus d1 upon d equal to V in dt in bracket 1 plus d1 upon d into d upon 2L, or IL1 equal to dt t V in upon 2L, and equivalent implications given is Rin equal to V in upon In, or equal to V in upon IL1, or equal to 2L upon d square t equal to 2L of d square. On power relation, In square equal to Rin equal to I0 R, or V upon V in equal to In upon IO equal to under root R in divided by R0, or under root RD square upon T upon 2L, or D in bracket under root 2L upon RT. From these equations, D1 is calculated under root 2L RT equal under root 2L upon R. These are the simulated waveform of the isolated your Cuck converter. The advantage of Cuck converter is a single switching device based isolated DC converter is the only converter in which the isolation transformer has an AC voltage across primary and secondary, and resulting in ideal operation of the high frequency transformer due to the presence of energy transfer capacitor in series of primary and secondary winding for blocking the DC voltage. This is the typically SEPI converter, single and primary conduction, where the output inductor made a couple inductor with the proper turns ratio. For getting appropriate DC output rate. Sometimes the multiple output is also there in this like, and these are the modes of operation when your switch is on, when the diode is on. So now coming to if the turns ratio and S upon NP, then the load side potential can be referred to the primary side of the high frequency transformer, and equivalent about it modified to simple non-isolated semiconductor. So C0 dash equal to N square C0, R equal to N Rn square, which VO dash equal to V upon N, ID dash equal to ISN, and IC dash equal to IC equal to ICN, and voltage across L1 equal to V in delta V plus E in minus VC1 minus VO dash into 1 minus dt equal to 0, and across L2 minus VL1 dt plus VC1 1 minus d into t equal to 0, or VC1 equal to VO dash into 1 minus d upon d, substituting the value from VC1. So we get Vn equal to VO 1 minus d upon d plus 1, or into 1 minus d, or VO equal to 1 minus d upon d, or VO upon VO Vin dash equal to NVD upon 1 minus d. So rate change of the input inductor current can be calculated during the switch on condition. L1 diL1 upon dt equal to Vn, VL1 upon Vn. So change in the input inductor delta IL1 can be calculated from delta IL1 equal to Vn dt equal to upon L1 equal to Vn dt upon FL1. The value of inductor for the given ripple delta IL1 is calculated from IL1 equal to V in d upon F delta IL1. The per unit ripple current in the inductor can be calculated delta IL1 equal delta IL1 upon IL1 equal to delta IL1 In, and V in dt upon L1 In equal to Rn d upon FL1, and equal to bracket in R 1 minus d square divided by N square F L1. Similarly, the rate change of the current in the secondary inductor can be calculated during the off period. Delta M upon dt equal to V upon Lm, V upon NLm, and the change in the Lm from this is a delta ILm equal to VO 1 minus d upon t and Lm, and the value of inductor Lm can be calculated as Lm equal to V upon 1 minus d divided by Nf delta ILm. For boundary condition between CCM and DCM, the value of minimum or critical inductance L1C equal to L1 minimum equal to VIN, V in d by F square L In equal to R in t upon 2F, or equal to R 1 minus d square divided by 2N square df, and L minimum equal to N maximum equal to VO 1 minus t divided by N F square Lm. So output voltage ripple delta V0 can be calculated during the on period in which the output capacitor CO is discharged through the load. The output voltage ripple is as delta V equal to I0 dt upon C0 equal to V0 dt upon RC0, that is equal to V0 d upon FRC0. The value of output capacitor can be calculated for a given ripple C0 equal to V0 d upon FR delta V0, and the per unit value capacitor across the capacitor can be delta V0 upon V0 equal to d upon FRC, and the ripple voltage across C1 can be calculated during delta VC1 equal to 1 upon C1 integration IL1 dt equal to IL1 1 minus d into d upon C1, or equal to V0 and d upon F RFC1, and the value of this capacitor can be calculated from for a given value C1 equal to NV0 D upon RF delta VC1, and the integral of voltage across the inductor L on LM must be 0. So L1 equal to V in dt plus V1 minus VC1 minus VO dash equal to D1T equal to 0, or LM across LM minus VC1 dt plus VO D1T equal to 0, or VC1 equal to VO dash D1D. So substituting the value of VC1 and as V in dt in plus in bracket V1 minus VO D upon D1 upon D minus VO in bracket close D1T equal to 0, or VO equal to n small n V in D upon D1, assuming power lossless system. So P equal to P in I upon N equal to D1 upon D1, and IL1 equal to IO upon D upon D1. Average current in the IL1 will be IL1 equal to IN equal to V in delta dt in bracket D plus D1 divided by 2L plus I, and ILM equal to V in dt D plus D1 on 2LM minus I. So adding IL1 and IL2 result ILM and ILM equal to V in dt in bracket D plus D1 upon 2L, and where L equal to L1 LM into divided by LM plus LM. So the capacitor average current is IC1 I minus ILM plus I D and divided by D plus D1 plus ILM I1 minus I D1 upon D plus D. By substituting IC1 in above equation, so it can be IL1 upon ILM equal to D upon D1. And from this equation, IL1 D1 minus D upon D equal to V in D T in bracket IL upon D1 divided by 2IL, or IL1 equal to D square V in T upon in 2L into IN, or IN equal to V in IN D square T divided by 2L, or IN square RN equal to IO square R0, or V upon V in equal to IO equal to under root R upon R1 equal to under root RD square T upon 2L, or D under root D under root 2L upon RT, where D1 equal to under root 2L upon RT. So these are the waveforms from the simulation for DC converter isolated. So now coming to Zeta DC converter, here we have an input inductor current, input coupled inductor with the, of course, for the isolate, and you can have multiple output also in this case also. And these are the typically couple of modes, one single secondary, whether device conduct or whether diode conducts like. And these are the typical waveform from the simulation. So coming to the analysis, these report quantity as VO dash equal to VO upon N, and C1 dash equal to N square C1, CO dash equal to N square C0, L2 dash equal to L2 upon N square, R2, R dash equal to R upon N square, N equal to N2 upon N1. So being a periodic waveform, the integral of inductor voltage must be 0. So L voltage across L1 is V in dt plus minus VC1 up into 1 minus D into T equal to 0, or VC equal to V in T upon 1 minus T, or L2 equal to V in minus VC1 dash minus VO in bracket dt plus minus VO dash 1 minus dt equal to 0. Substituting the value of this, so VO equal to NVD1 V in T upon 1 minus D. The rate change of inductor current is calculated during DIL1 equal to dt equal to VL1 upon L1 equal to V in upon L1, or the change in inductor current is delta IL1 equal to V in dt upon L1, or V in D upon CFL1. The value of inductor current L1 can be calculated from the given input current. So L1 equal to V in D upon F delta IL1. So similarly, the rate change of L2, the current can be calculated during off period. So delta IL2 equal to VO dash upon L2 dash, or change in inductor current from delta IL2 dash equal to VO 1 minus D T upon L1, or equal to V0 1 minus D FL2. The value of the output filter inductor current can be calculated L2 equal to V0 1 minus D, typically F delta IL2, and the ripple voltage across L1 can be delta VC dash equal to 1 upon C dash in bracket dt IL2 dt, or equal to IL2 dt upon C1 equal to IO dt upon C1, or equal to V0 divided by R O into R dash CF. And the value of capacitor can be calculated for a given value ripple. So C1 dash equal to VO dash T upon R dash F delta VC dash, and the output ripple current across the capacitor can be calculated from the output inductor current, which is equivalent to delta V dash equal to delta V delta Q upon C0 dash equal to 1 upon C2 dash V0 into delta IL2 dash divided T into T by 2, or delta V2 dash equal to T V0 1 minus D into T and divided by 8 L2 dash into C2, and per unit voltage will be delta V upon V2 dash equal to 1 minus D 8 FL2 C2 dash, and the value of output capacity C0 equal to 1 minus D T square divided by 8 L2 delta V upon delta V0. And for the boundary condition between CCM and DCM current, triple inductor current must be twice of theirs. So L minimum equal to L1 C equal to V in dt upon 2 IL1. Similarly, critical value of L2 dash L2 to Z L2 V0 1 minus dt upon 2 IA0, that is equal to 1 minus d R1 dash divided by 2F. So if VC1 is average C1 capacitor voltage, the capacitor voltage delta VC will 2 VC, then critical value C minimum C1C equal to 2 FR dash d upon 2 FR dash. Similarly, critical value of capacitor delta V2 VC C2V C equal to 2C minimum, the 1 minus d upon 16 L2 dash square L2 dash F square, that is equal to 1 upon 8 FR. So the relation between the input output voltage can be V in PT plus minus VD into D1T DTP. So VC dash equal to V in upon D1 of T, and voltage across L2 V in plus VC dash C1 minus VO dash to DT minus VO dash D1T. Substituting the value equal to 0, substituting the value of Vcn, so V becomes V in plus V in dash D upon D1 minus VO dash D plus D1 equal to 0. So VO dash upon Vn equal to D upon D2, or VO dash upon V1 equal to V upon V1 is and D upon D1. And assuming the lossless system, power quality, the power equality PO equal to Pn, IO dash upon In, D1 upon D, or IL2 equal to IN upon Vd. So average current in inductor IL1 equal to V in dt upon D plus D1 upon 2L1 minus I, or average current into inductor 2 L2 IL2 equal to P in dt in bracket D1 plus D1 divided by 2 L dash 2 plus I1. Adding these two results in IL1 plus IL2 dash equal to V in dt in bracket D1 plus D divided by IL, where IL equal to L1 into L2 divided by L1 plus L2. Coming to the solved problem, the first solved problem is an isolated DC-DC converter is operating with a minimum duty cycle of 0.54 in CCM. The supply voltage 300 volt DC and required output voltage 48 volt at 9 ampere. The operating frequency 50 kHz. The peak to peak ripple L1, L2 20% of their respective average current. The peak to peak ripple voltage C1, C2 are 240 millivolt respectively. If the output voltage is 100 volt, calculate value of L1, 2, value of C1, C2 and output capacitor. So just using the formula here, I mean the voltage output is given, so duty cycle 0.45. So we can find out ID equal to IL1 0.807, IE2 equal to IL2 10 ampere, delta IL1 equal to 0.1614 and IL2 comes like 2 ampere, ID1 is a 240 upon 300, it comes 0.1614 ampere, and putting this relation getting a turns ratio, it's 0.19556 for triple and 5. It becomes the primary to secondary is 5.11. So delta IL1 to 0.2 IL1, that becomes 0.1614 and IL2 this, and from this we get L1 16.875, L2 equal to 0.264 millihenry. Similarly, CO equal to 1 minus dV upon L2 square, so it comes 50 microfarad, and C1 comes V in D NV square D1 upon RF 1 minus D delta VC1, it comes 176.25 microfarad. C2 comes V0D or F delta V2 C2 equal to 900 microfarad, and L1 is putting a value 16.728 and L2 pure putting a value V0 1 minus dt of L2 is come 0.264 millihenry. Coming to problem 2, in flyback DC-DC converter, V in 24 volt, VO is 5 volt, I equal to N, F is a 100 kilohertz and equal to N1 upon N2.4. Calculate the maximum value of magnetizing inductance for DCM. The output filter capacitor if permitted ripple is 1% and duty cycle. Given flyback all data, so we get the putting a value, we get the D equal to 0.4 and R equal to 0.5 ohm, LM P upon V or D upon R2F, that is 4.04 microhenry, C equal to V upon D into FR0, that's 680 microfarad, and D equal to 0.34. Coming to numerical problem 3, in an isolated SEPIC single primary converter, DC-DC buck boost converter, supply voltage 48 DC and the required output voltage 360 volt 3 ampere, operating frequency 50 kHz. If the peak ripple current L1 to 20% of their respective average current, peak to peak ripple C1 C2 200 million, calculate the value of L1 L2 and C1 C2 and transform potential. So all the values are given here. So we get V1 IN equal to power by V, so 22.5 M, R equal to 360 by 3, we get 120 and RI get 2.13, and the turns ratio we get from this N equal to 0.75, L1 we get V in D upon F delta L 0.1066 millihenry, L2 equal to VO1 minus DFN delta L, it becomes 0.8 millihenry, as C1 equal to N PD0 and Rin equal to 1.32 microfarad and C2 equal to VO0 becomes 0.41 microfarad. Coming to numerical problem 4, the output of isolate DC-DC buck boost converter is P equal to 25 at resistive load of 1.25 ohm. The conduction drops the transistor under order 1.4 and 0.7. Transformer turns ratio is N equal to 1 and 1 upon N to 6. Consider the duty cycle of 0.5. Calculate the average input current and the efficiency. So all the data are given B in and all that. And from this we can calculate the typically the I prime. We calculate primary voltage and 1 upon N2 V secondary 154 Vn equal to V primary 155 I primary and 2 upon I that comes 3.33 and I in 2D I primary 3.3 and Pn equal to Vn I in 518 watt and P equal to P 500 watt and efficiency it comes at 96.40%. So coming to problem 5, a flyback converter operates switching frequency of 50 kW. The input voltage Vn 24 volt and output voltage 12 volt. The transformer turns as N1 upon 2 to 1 to 1. Assume the converter operates in continuous conduction mode with the average output current 2 ampere. Efficiency of converter is 90%. Calculate the duty response. So duty cycle of the flyback converter in CCM is D equal to P out upon N1 divided by V in N2 plus N1. So subtracting the value D comes 0.5. Thus the duty cycle is 50%. Now coming to problem 6, a flyback converter operates switching frequency of 50 kW. Input voltage 24, output voltage 12 volt, and the turns ratio 2/1 and operate CCM and with the average efficiency. So here all typically peak current of side is I peak equal to I out upon N2 upon D. So substituting value I peak equal to 2 into 1 5 4 ampere and I peak is 4 ampere. So 7th principal converter with a Pn equal to 24 volt. Transformer has a transfer and 1 upon 2.1. Duty cycle 0.4. Calculate the output voltage. Output purposefully is V out equal to 2D V in and 2 upon N1. So V out putting value it comes 9.6 volt. Now coming to 8th problem, a half bridge operates V in equal to 300. Transformer turns and 1 upon 3 to 1. Duty cycle 0.45. Determine the output voltage half bridge is V out equal to D V in by 2 into 2 1 N1 and putting the value it comes 22.5 volt. Problem 9, a forward converter operates Pn equal to 36 and deliver 9 volt to load of R equal to 4 ohm. The turns ratio at 1 upon 2 1. Switching frequency 50 kW and the duty cycle 0.5. Assuming the magnetizing tense transformer Lm equal to 500 microhenry and the average magnetizing current. Calculate the magnetizing current triple is delta Im Pn D Lm upon Av. So delta Im is 0.27. Average magnetizing current is delta M by 2, that's 0.36. So this becomes 0.36 ampere. So problem 10, a push-pull converter operates Vn equal to 24 volt and 1 upon N2 3.1 at 50 kilowatts and to 15 volt and load curve varies from a minimum to 2 ampere to 6 ampere and using the efficiency 88%, calculate the primary current range. So primary current related to IP equal to I out of N efficiency N2 upon N1. So put I out 2 ampere, so it comes I primary putting value 6.81 and 6 ampere, it becomes like 20.43. So IP ranges from 6.81 to 20.43 ampere. These are the unsolved problem. One can solve with the answer these are given, and these are the references which followed. And thank you very much.